In a universe built on perfect symmetry, life made an unexpected choice. From the first stirrings of chemistry to the molecules that began to shape their own destiny, one quiet mystery endures. Why did life choose the left hand? The origin of homochirality of L-amino acids has long been a mystery. Amino acids have optical isomers termed L-amino acids and D-amino acids, which have structures that do not overlap like left and right hands. But natural proteins formed on ribosomes are composed of L-amino acids only. Amino acids may have been seeded by small celestial bodies as chemical materials. However, sample analysis from asteroid Ryugu by Hayabusa 2 of Japan and from asteroid Bennu by OSIRIS-RX of NASA did not reveal significant amino acid enantiomeric excesses. This does not necessarily agree with the most prevailing perspective that a slight enantiomeric excess of L-amino acids present on primitive Earth is the origin of homochirality. Notably, this perspective ignores two important factors. The first is rapid amino acid racemization, which is the process of converting optical isomers of amino acids into a 50-50 mixture of L and D amino acid enantiomers. Even if a slight enantiomeric excess of L-amino acids existed on primitive Earth, how could it overcome the speed of racemization before life was created? The second is the continuity of biological evolution. For example, it must provide a consistent explanation for how the protein synthesis system, composed of L-amino acids, seen in modern ribosomes, arose continuously from simpler forms in terms of the continuity of biological evolution. Aminoacylation is the first reaction in protein biosynthesis and consists of two steps. In this two-step reaction, aminoacyl AMP is used as a reaction intermediate. In the first step, ATP is used to synthesize activated aminoacyl AMP. In the second step, amino acids are transferred from aminoacyl AMP to tRNA. In modern systems, L-amino acids are acylated by aminoacyl tRNA synthetases to form aminoacyl tRNAs. The L-amino acids are then linked through ribosomes to form proteins based on the information presented by mRNAs. Thus, aminoacylation of tRNA is considered to be critical for the transition from the putative RNA world to the theater of proteins. RNA minihelices are progenitors of modern tRNAs. Koji Tamura and Paul Schimmel proposed a non-enzymatic RNA aminoacylation model. Using aminoacyl phosphate oligonucleotides, which contain the same partial structure as aminoacyl AMP, together with bridging oligonucleotides. This model is composed of a simple, minimized system that captures the essence of tRNA aminoacylation without the assistance of enzymes. In this system, the amino acid is transferred from 5' phosphate to the 3' hydroxyl group via the transition state corresponding to the highest potential energy along the reaction coordinate. Surprisingly, in actual experimental systems, RNA minihelices are aminoacylated far more efficiently with L-amino acids than with D-amino acids. Molecular dynamics simulations based on quantum mechanics and molecular mechanics (QMMM) provides atomically detailed structural information of reaction intermediates and transition states. The simulations were performed for the chiral selective aminoacylation of an RNA mini-helix. Through simulations based on quantum mechanics, detailed chemical structures corresponding to the progress of the reaction, including the transition state, were revealed for the first time. The distance between the negatively charged 5' phosphate and the positively charged amino group of L-alanine was shorter than that of D-alanine. And the energy barrier for L-alanine was 9 kilocalories per mole lower than that for D-alanine. These results would be a plausible mechanism previously unexplained for chiral selectivity in the RNA mini-helix aminoacylation. Therefore, a strong possibility exists that primordial RNA aminoacylation led to preferential homochiral protein biosynthesis on early Earth. Thus, L-type amino acids are likely to be bound to the primitive tRNA, and by linking these together, proteins constructed from L-type amino acids would be created. Perhaps life's left-handedness was never mere coincidence, but a quiet decision made when matter first began to choose. That ancient choice still echoes in every molecule, in every pattern of what we call life. This is life's left-handed mystery.